Hey everyone, welcome back. In this video we're going to be looking at the Yuichi A290, and this is a bi-radial horn. I've offered the 3D CAD files for this on my site for about 4 years now, and so this video is going to be looking at some actual test data. So we had built these on our CNC, and we also 3D printed some custom throat adapters to help smooth the transition. So normally the horn has a square entrance on the horn throat, and so we've just printed these adapters, which are also available on my site to download if you want to 3D print these. And so the idea is that it provides a smooth transition from the circular throat of the compression driver going into the square, it's 5 by 5 centimeter square throat entrance. And so you can see here the pictures are showing that has kind of a lofted extrusion that produces a smooth physical geometry in the throat there. So the horn is a 300 hertz cutoff. It's been around for about 4 decades, and it's quite popular for large format studio monitors kind of back in the heyday, and so people also use them in home audio 2-channel listening. And so the idea with this horn is that it provides wide horizontal off-axis coverage. And so in this video we're going to test 3 different compression drivers using the throat adapter in either the 1.4 or the 2-inch throat. And so the 3 compression drivers that we'll be testing today is the RCF ND 950 shown here, which is a 4-inch voice coil titanium diaphragm. The other compression driver it's also a 1.4-inch throat. It's the SB Audience 65 CDT, which is a 2.5-inch titanium diaphragm. And then we're using our rear cover. So this is also available on my site as well as a 3D CAD file for 3D printing, which is going to enlarge the rear chamber. So that lowers the FS of the compression driver from about 450 hertz down to about 290. So you can see here it just enlarges that rear chamber, and then it provides a venting out the back. So the 3D CAD file comes in 2 versions, either a completely closed off version and also a vented version. So the vented version will be the default version that you would use unless you're using it inside of a base enclosure where there's air pressure that you need to seal against, protect the compression driver against the air pressure inside the base cabinet. So okay, so we'll get right into it. So to start off, we mounted the RCF ND 950 1.4-inch throat compression driver onto the Yuichi A290, and it produced the following frequency response. So it's using a 4.38 millisecond gate, and so the responses you can see here, it has a bit of a downward trend, and we're about 10 dB down at 10 kilohertz. And then we have the normal breakup that you would see, which is normal with this compression driver coming into play. So this is more typical of what you would see with the constant directivity type style horn, where it has consistent wide upper treble coverage. And so this isn't really an issue per se. It's more in the fact that the energy of the horn is being distributed off axis instead of on axis. And so with my ES bi-radials, they have a narrowing directivity as you move up into the upper treble, which provides a flatter frequency response on axis. Okay, but if you were to use a horn that has wide coverage in the upper treble, so above 90 degrees and up to like 120, then you're going to see a falling response on axis because that energy is being redistributed to the off axis. Okay, so it's not that the horn doesn't load well in the upper treble, it's that it's being channeled off axis instead of being focused on axis. So okay, so the next compression driver that we tested was the SB65 CDT, and again you can see the falling trend. Now this peak here, I think it's at around 4K. This is part of the driver, it's not inherent in the horn, but we do have a very nice flat frequency response. The other thing I should mention too is that this here is it shows it as like a smoothing. This is due to the 4.38 millisecond gate. I'll show later in this video what it looks like with the gate removed, and so it'll give you a little more clarity as to what's happening near the cutoff of the horn, which is 300 hertz. Okay, so the 65 CDT, similar kind of frequency response, and then we have the breakup occurring at 17 kilohertz. And so this diaphragm is a 2.5-inch diaphragm versus the 4-inch on the RCF. and so it's going to have the breakup pushed up quite a bit higher as a result. Okay, so just seeing here, the gating, I removed the gating just to show what's happening, and so you can see here near the cutoff of the horn there is a bit of a bump, and so we're left with a question of whether that's inherent in the driver or if that's an attribute of the horn. Okay, so that's something that we're going to discuss in a little bit. So the next thing that's quite interesting, and there isn't any data on this horn online in regards to an off-axis colored polar map, and so I did measurements at 5-degree increments and produced this colored map. Now I had to limit the upper part of the bandwidth to 15 kilohertz, which is shown here, just so that we get the proper scaling. Otherwise it was the breakup mode in the RCF ND 950 was causing some scaling issues with this polar map, and so by limiting the upper frequency to 15 kilohertz, it gives us a little consistent color map to what you're used to seeing. So just in comment on the actual results here, we see a bit of a narrowing in the 500 hertz region, but then it stays consistently wide. You'll note that it is 120 degree listening window right up to we'll say about 5 kilohertz, where we see it gradually start to narrow, and then by 10 kilohertz we're at about a 90 degree listening window. Now as far as consistency, the waterfall 1 map within ARTA kind of clearly displays things a little easier as far as how consistent the off axis is with the on axis. And so you can see here, even with the waterfall 2 map, it's probably the better way to look at it. So as you move off axis, you can see some increase in output in various parts of the frequency spectrum. So at like 5 kilohertz there, you can see it. Actually, there's an increase in output as you move off axis. So, but generally it's wide, generally consistent off axis. There's certainly much worse horns out there, so it does a good job of getting that coverage nice and wide and even maintaining that width into the upper treble. Now you can see here there are some artifacts being produced at the 120 degrees off axis, which we can talk about in a bit, but overall what this is going to do as far as the subjective listening quality, it's going to provide a very wide soundstage width. And then if the horn is free of any coloration and resonances, then we're going to get very good soundstage depth as well. So the next thing I did is I tested the off-axis colored polar map with the 65 CDT compression driver. So this is the one with the 2.5 inch diameter diaphragm, and so you can see here it's going to provide a little more accuracy in the upper treble simply because there isn't breakup until 17 kilohertz. And so I would say this colored polar map is a more true to life representation of the horn itself. Anytime you get breakup modes, it's going to affect the off axis of a horn just because it's completely out of control. You're going to get spurious sounds coming out of the throat at different directions, and so this is going to be more representative of the horn itself. And so showing the same the waterfall 1 and the waterfall 2 there, it's showing kind of in the upper treble we're going to have some irregularities, but overall it's providing wide coverage. And then I think even more pronounced is the edge diffraction artifacts that we're seeing in the upper treble there at the 60 degrees off axis. Okay, so the next thing I did, in order to do time domain, like burst decay, waterfall, I like to apply some EQ to flatten the response so that we get more representation of a real use case, after the crossover has been applied and we have a flat response. So I applied a 8.5 dB contour circuit centered at around 6.5 kilohertz. So you can see here, this is the resulting effect of the contour circuit, and so this is the overlay between the raw response in red and then the effect of the contour circuit in green. And so this is moving forward, this is the contour circuit that I had for all the measurements moving forward. And so just keep that in mind. So the horn clearly does need some EQ, similar to what you would need with the constant directivity horn. And so that's just something to keep in mind when you're trying to implement a crossover for this horn. Okay, so burst decay, it's not going to really show up anything in relation to the horn unless the horn actually has significant resonances within the horn. And so what we would typically look at is just comparing the two drivers and seeing if something consistently shows up between the two drivers. And we do see a bit of a resonance occurring at around 1 kilohertz, even between the two drivers there. And so that might indicate that there might be a subtle resonance occurring inside the horn. The CSD waterfall for the RCF is shown. Nothing really of concern with that. You have your typical breakup coming through there. Harmonic distortion, so this is with the EQ applied. Testing it at the 9, I believe it's 80. I'll just see here if I have it wrote down. 85 dB SPL at 1 meter. And this is with the RCF ND 950. So you can see very low distortion, but you can see that the harmonic is trending upwards, and that's directly a result of the contour circuit EQ that we applied. And so that's something to keep in mind, that when you are applying EQ to the horn, that you're going to get a proportionate amount of increase in distortion for the region where you're boosting that EQ. And that shows up very clearly in the IMD, where you see the noise rising in proportion to the contour circuit that we applied. So you can see here the CDT, the SB audience driver, is doing quite well for distortion. So subjective listening was actually quite interesting, and I want to be really careful how I explain this. So it's really good that I had tested the two different compression drivers, because if I had just tested the one compression driver, I found an issue with the smaller compression driver, the 65 CDT. So even with the rear chamber lowering the FS to around 290 hertz, it still produced what I would call like a resonant sound character in the 300 to 600 hertz region. And so I would have, if I had just tested the SB audience compression driver, I would have falsely attributed that to the horn itself, thinking that the horn has first order reflections occurring near cutoff, and but when I switched to the RCF ND 950, which is a larger 4-inch diameter diaphragm, the coloration went completely away. And so it wasn't the horn causing the coloration that I was detecting. In fact, what had happened is when I went to the larger compression driver, there was incredible authority in that frequency region, in the 300 to 600 hertz frequency region, where and that's the male vocal region. So with soundtracks with male vocals, there was just a tremendous presence and scale and authority to the male vocals with that combination A290 and then the RCF ND 950. The same occurred when I switched out to the large format. It's the BNC I'm trying to remember, DCM 50, which is another large compression driver. Same thing, great male vocals that really came out with just like an impressive, entertaining sense of scale to the male vocal region. And so just kind of a lesson. When you're testing horns, definitely try a variety of compression drivers, because you may falsely attribute kind of a weakness to the horn when in fact it's the driver. Okay, so now listening to the upper treble quality, again, if I was just listening to the RCF, which is the larger diaphragm, 4-inch diaphragm, the upper treble sounded kind of diffuse and fuzzy. It didn't have the clarity that was, I would call, acceptable. But when I switched over to the SB audience 65 CDT, the treble quality was restored, and so I had tremendous clarity despite the dispersion fins. I know they're not technically dispersion fins, but the vanes, if you want to call them that, I was concerned that those vanes would introduce issues in the treble, but that wasn't the case. I was getting really nice treble clarity, detail. And so again, if I had just listened to the RCF, I would have thought that that fuzzy treble quality was attributable to the horn, but by switching to the smaller compression driver that does better in the treble clarity was restored. And so just kind of lesson for me, lesson for you as well. If you're testing and you're evaluating, make sure you do a thorough investigation on what you're trying to evaluate. So the other driver that I tested in this series was the DCM 50, which is a BNC. So it's the one with the paper diaphragm with the phase plug. It's a 5-inch diameter paper cone inside the compression driver. And so this compression driver, you can see it here, the DCM 50. So this is the response of the DCM 50 on the Yuichi A290, and you can see here that with the EQ applied, it still wasn't really, it had kind of a pretty significant dip there through the 3 or 4 kilohertz region. So this compression driver, I would say it did well as a mid only. The upper treble, even after the contour circuit, it didn't have the clarity and resolution in the treble that I was hearing with the ES290 biradial and also the Azura horn AH340. So I have the AH340 here as well, which is a 2-inch throat exponential with a rolled lip. And so this is a really good combination if you're interested. Highly recommended for point source. It does upper treble up to 11 kilohertz, but there's a nice little peak there at 11 kilohertz where at the end of the day, my hearing at my age at 42, I probably can hear up to maybe 13 kilohertz, so I wasn't really missing a whole lot of that last little bit of upper treble. With this, it's technically a mid-range only compression driver, the DCM as mid-range, but it does actually quite well, covering the whole spectrum from, in this case, 340 hertz right up to 11 kilohertz. So that actually sounds really good on this horn. Not so much on the A290. For whatever reason, just I think mainly because of the way that it has that falling response, it just couldn't produce enough upper treble output to have a balanced sound there. So so the conclusion here, now I did a little bit more testing with the SB Audience 65 CDNT or CDT. And I found that if you did high pass filter at 500 hertz using an LR4 filter, that resonant sound character that I was getting had completely disappeared. And so if you're looking to use a 500 hertz crossover, then I found that the SB Audience 65 CDT was completely suitable on this horn, providing great upper treble clarity, and it didn't require a super tweeter. It was just overall a good driver, and it's been a consistent performer with other projects. As you know, I'm using it in a variety. So the 65, the Neo version and the ceramic version. So I've tested both, and they both have identical response. And so the only difference obviously is the magnet. And so if you are looking to save, I think it's around $100 per driver by going with the ceramic version. And so that's something that you might want to consider if you're on a budget. But now with the RCF ND 950, so that's the 4-inch diameter diaphragm, it does tremendously well. If it was me and if I had my preference, I would go with the RCF ND 950 and let it cross at the 300 hertz. But there's some caveats with that, and I'll get into that. But I would use the RCF ND 950 with a super tweeter such as the Fostex T90A, and I think that would be a good solution. You just leave you don't use a contour circuit. You just let that naturally fall off in the upper treble and then come in with that super tweeter at around 8 kilohertz. I think that would be a really good solution because you get that great transient detail of the super tweeter, and then you get that male vocal authority down in that 300 to 600 hertz region. So that seems like a really good solution. I think it's going to be a little more costly to do, but I think if you have the Yuichi A290, that would be my pick there. So Now, I mentioned about the caveat with doing that. Now, I did an ungated measurement with the RCF ND 950, and one thing you can see, it goes right down to 300 hertz, or you can zoom right in there. If you zoom right in, it's probably 290. So kudos to Yuichi for designing a horn that nails the FS as described. But you'll notice that the steepness of that slope is obviously very steep. So what you need to do is, when you're doing your low frequency and you're doing your low pass filter on the bass section, you're going to need at least an LR4 or an LR6 high or low pass filter to match the steepness that you're seeing with the high frequency there. And so I see that's a common mistake that many people make, is they'll put like a second order on the low frequency and a second order on the high frequency and then call it a day. But what you'll end up with is the low frequency will just continue on and on and on, and it'll still be output at like 5 kilohertz from the woofer. You need to cut that off, use very large value components in the capacitors, and you know, it's going to take some finesse and some, not just textbook crossovers, but you're going to have to really look at the response of the woofer near the crossover point and make sure you have what's called symmetry there. And that's going to and when you have that symmetry, you're going to have the coherency that everybody is after for a simple two-way. So okay, so future testing. So I have some 18 sound 3-inch beryllium compression drivers that I plan on testing on this horn. I did do a blog post on that driver, so you want to check that out. I'll be doing a video on it as well. So and then also customer has sent me brand new inbox, still sealed from the factory, TD 4003s. And so you can see here some pictures. I'm the first one to open the box and check out this beauty of a compression driver. And so it's unfortunately it's a 1.5 inch throat, and so I had to get some adapters printed to do that unique throat size. And so I had some adapters printed for the Yuichi A290, which we're testing today, and also for the ES290 and ES450, you know, a throat adapter to go from 1.5 up to 2 inch. So get some test results on this compression driver and see how this world-renowned compression driver does with my testing. So so that's it. Yuichi A290. So 3D CAD files are on my site for the special throat adapters, and also the rear cover for the CDT and CDNT there from SB Audience. So I think I covered everything off. So take care and have a great day.